Right, good morning, another video. Right, getting close to the end now. So this is the proportional integral control, and once again I'm to your right here, and this is all set up as before. But the whole point of this lab was to investigate Ziegler-Nichols methodology of getting the or determining the values of the Ku and Tu constants in a control system, because it can take ages. If you don't use this formula, then where do you know where to start? And so the whole point of the Ziegler-Nichols is to actually determine those, and so that you can insert this into your system, and then you can play around with those numbers in order to try and get a better performance. So what you'll see in the presentation that goes with all of this, when you've been clicking these videos, you'll see that I've produced all the tables for the different pulley ratios, and in amongst those tables, right at the bottom of each one, you'll see the Ziegler-Nichols settings for proportional integral control. Now I've got the system set up for a 1-to-1 ratio here. And what we're going to do is set them up in accordance to that. So we've got a K value of 2 and a time constant of 0.296. So let's enter this. I'm selected the proportional integral control, which I think is option number 9. Let me just go back and exit that just to see. Yes, this was run proportional integral control, which is option 9. Which is what we're doing now, and I'm now going to enter those values as per the data that we've calculated from the previous experiment. So I'm going to take option 2 and change the gain value K, which now becomes Ku, to 2, and remember this is for a 1-to-1 ratio. And the time constant, so I'm going to change, selecting option 3, and we've got the integration time constant, which in this case is 0.296 seconds, or in the HMI it's in milliseconds, so we're going to enter 296. So we're going to enter that. We're now going to move the, I've got all the gains and attenuations is set to 1, and we're going to move the compass to the south position, which it in fact already is. I'm just going to move it to north just to make sure it's all working properly. So let's go to 8, there we go. That's fine. Just going to move it to 9, which is the south position, and run the 1-to-1 ratio. And now I'm going to run the algorithm. I'm just going to reset that to 0 because I was messing around with this yesterday. And we're going to run the algorithm, and there we go. Right, interesting response. So let's just bring this down a bit and run the algorithm again. So we're just going to put it into south position, and I'm just going to run the algorithm again. Right, that's looking good. Let's move this across so that we can actually see a little bit more detail. Next, go back to south again using option number 9. And now we're going to run the algorithm again. Right, now then, so what's going on here? Well, there's a number of things, and what you'll also notice is the compass. You might just be able to see this. I'm not too sure whether you can see what's going on here, but the compass is actually moving every now and again, one direction or the other. Let's see what's happening. So the signals I've got in here, the first one is the error signal, and this is the proportional part of the result. Now neither of them have saturated because we've only got a K value of 2, but what's going to be really interesting is when we look at the integration value, which is absolutely fascinating. So what have we got here? These are both set to 1 volt per division. This is the error signal that's coming in, and you'll see that we've actually got an initial start, fairly linear response. So that's our maximum speed of transfer. It's overshot at around about, let's see, 0.8 seconds-ish, which actually ties in 0.7 seconds, which is what we did on the calculations prior to this. And then we've got a very big overshoot, and then it comes along and we've got so one overshoot here and another overshoot here, and then it's stabilized. Now, so what's actually going on from the integrator perspective? So I'm just going to move my scope probe now, and I'm going to look at what's actually in the integrator on the channel 2 here. So I'm going to run the experiment again. So we're going to go exit the algorithm, and I'm going to move the compass to the south position, and then I'm going to run the algorithm. Now this is fascinating. So the integrator is adding up all the errors. So at this point in time, this is actually, remember, there's our north position in the center. I might put a bit of gain on this actually, so so that we actually see it in a little bit more detail. Let me just exit this. I'm going to put some gain onto channel 1, which is the error signal. So let's number 4, and we'll change that to 2. It gives us a multiplication factor of 2 on the display, and then we're going to go to 9 to move the compass south, and then we'll just run the experiment again. There we go, and so we can see this in a little bit more detail. I hope you guys can see it in a bit more detail. So this is the 0 line north position. So what you're going to see is, if you look at the point where it starts to cross over, this is a negative error. So we're getting a constant negative error. So what you'll see is the integrator is adding up that negative sum, and it's actually built up quite a large value here. And then once it's gone past the 0 point, it's now actually taking this error off, and so it's now going back. So the integrator is now it's got a negative number going into the accumulator. Now it's taking away the value from the value in the accumulator. So what you're seeing here is, first it's actually on one side of north, and then all of a sudden it's gone past one side of north and it's now on the other side, and now it's going to subtract from the accumulator, and once again you get to this point here and it's doing the same thing. So if you look at these key points here, you'll see a change in the direction of the integrator value, and this is really important because the reason this has got such an enormous swing on it, let me just run it again. I don't know how well you can see this. I hope you can see how big a swing it is. So let's just exit that, and we'll run that again, going to 9. And what I want you to do is watch what's happening on this pointer, because it's represented on the screen here, but it's also interesting to actually observe. So we're now going to, we've gone to south, and we're going to run the algorithm, and you'll see there's a massive response back here. And that's because all of this value, this is where it's crossed over, but the integrator's still actually got a huge amount of data in it, and it's got to be removed incrementally through the algorithm by integration. And so what's happening is it's got this massive swing in order to get rid of all of this, the number that's actually in here, to get it to go back through 0, and it gradually accumulates to a small number. Now the reason the pointer is actually jittering is at the moment it's here and it's moving like this, and that's because this number, this error number, is not exactly 0. And so the accumulator in the integrator is actually running all the time. And so this is where you start to get this slight jitter. So it makes it questionable sometimes on very slow systems in actually whether in fact integrators are actually worth using. So I would raise that question to students, is, looking at this response, is it better than when we just had K? So what I'm going to do now is I'm going to increase the time constant to a large number. And what it does is it effectively removes the integrator, because when you look at the constants that's used to multiply after the integration software takes place, it multiplies by this k divided by ti. Well, if you make ti huge, then in fact what happens is it means it's virtually multiplying the integrator number by quite a large, by a very, very small number, and therefore it starts to tend towards 0. So it becomes more like our KR proportional system. So let's just do that, and let's just see what the response. So if you take, if we now exit the algorithm, and I'm now going to change the integration time to 10 seconds rather than 0.296. So let me just do that now. Let's see, that's option number 3. And I'm going to put in 10,000, which is effectively 10 seconds. And I'm going to move the compass to the south position. And I'm now going to run the algorithm. And now you'll see what it's done is the integrator has got nothing in it, hardly anything in it, but the integrator is still running. Yeah, so you still get small errors, but it's a much better response. So if I was to move this around, it's actually working pretty well. So it suggests to me that in fact maybe PI control systems in this particular application isn't actually necessarily the best control system for this condition, for the servo and the way it works. And this is why you need to understand your hardware when you're actually designing these algorithms. So let's just put this back to the original 0.296, so 296 milliseconds. I'm going to go 3 and 296 for my integrator time, that's 296 milliseconds. Move the compass back to north. Let me just make sure it doesn't touch on that. And I'm going to run the algorithm. And now you'll see once again you get this massive integration. But does it function as a system? Well, it's actually responding really well, but it always gets a bit of overshoot. But it actually responds a little bit more quickly than it would if the integrator wasn't there. So we've been looking at this from an extreme perspective, but maybe that in real control systems never work because they should be tracking all the time. So there's these counter arguments about this. So it depends. When you first switch on the system, you'll get a really bad response, but then once it's actually active, you're actually getting a pretty good response to this. So but you see the overshoot that just occurred there. And also the larger that integrator is, the more this starts to jitter a little bit. So I just want to show you all of that so you get a really good idea of what's going on. So what we're going to do now is I'm going to change the ratios, and we're going to perform the same experiments and just see what happens with those. Just a matter of interest, we will just look and see what's happening as the final output that goes to the servo. So it's a summation of the error, the k times the error and the integrator. So we can actually see that on the scope as well. So let's just see what happens. I'm just going to move the compass to the north position, the south position, get it out of the way, there. And we're now going to go 1 to run the algorithm. Right, okay. And what you'll see here is flatlining, which is great to see. So you're getting this flat line. So this is remember this is the summation of the proportional component and the integration component, which has been modified by the constant Ku over Tu. But you'll see a flat line here, and that is showing that this has actually saturated the converter. So if I was to now put a division by 2 onto channel 4, so let me just do that now. So let's go to exit that. And I'm going to divide, I'm going to put a 0.5 gain factor onto channel 4. I'm going to move the compass to the south position, which is 9. And I'm now going to run the algorithm. And now you'll see it hasn't flatlined, which is great. And now I can see the whole of the maths that's actually going on inside the actual algorithm. So I hope that makes some sense. So what we're now going to do is we're going to change the settings, and we're now going to a much slower system, and let's see what the repercussions of that are. So let me just take this off of here, and the twirly noise you hear in the background possibly is my power meter that's on the wall. Right, okay, so now we've got the slower ratio, and now I'm just going to put this back to the original settings so we can actually look at the error and the proportional part of the signal. And let's see, so looking at the data that you were provided with in the PowerPoint presentation, we have a K value of 4.4, and once again we've got 296 milliseconds. So I'm going to put those numbers in. So we've now got the K, so I'm into 2, option 2 is 4.4 according to Ziegler-Nichols, and I'm just going to put the we've already got 296 in the integration time, and we're going to move the compass to the south position. And remember, it's a much slower system now, so we're working on the ratio 2:1. And okay, just done a quick check on what was going on there. Hence the sudden change in the video. There's a small issue with the floating-point maths, but I'm not going to delve into that at this stage. But it's all to do with the direction for which it starts. But anyway, what I'm going to do is go exit the algorithm and move this to the south position, which is 9. And in order to get this to not have a problem, I'm just going to turn that slightly here. And now what I'm going to do is run the algorithm. So once again, we've got K is 4.4 and TI is 296 milliseconds. And I'm now going to run the algorithm. And now you'll see it's a really, really slow response, not very good. And if I move it, then let's just see how well, but it is actually responding really well to actually small movements, which is actually ultimately what it's designed to do. But it's a very, very poor system when it comes to being at its extreme. So let's do that again, X, and move it to the south position, 9. There we go. And once again, just looking at this, you'll see that these have totally saturated on here. This is the proportional output. I'm just going to put some attenuation onto that. So I'm going to put an attenuation of 5 on there. So let's see, attenuation on, that's the integrator, that's 6. 6. And I'm just going to put some attenuation on that. So I'm going to bring that down by a factor of about 5. So I'm going to put 0.2 in as an attenuation factor, and or it's like a gain of 0.2, attenuation of 5. And now we're in the south position, and I'm going to run the algorithm. And now we can look at this in a little bit more detail. There we go. So here you'll see we've got the gradual negative accumulation here. There's the first bit, so we're actually adding to the accumulator here because the error is always in one direction. Now it's in the opposite direction because that's our changeover point, so now it's going in the opposite direction here. And so once again we're still in we've just gone over the transit line here, so it's starting to go negative again. And similarly here, the transit line starts to go positive again. So very poor response from a steady state starting off with an extreme change, but actually pretty good from performance when you look at it when the error is actually quite small. Okay, and now what I'm going to do is exit that. I'm now going to put this onto the much faster response, and put that onto there. Okay, So now we've got the fast response, and if we look at the formulas for this one, this is a K value of 0.72 and 336 milliseconds. So I'm just going to put those in here. So we've got, I'm just going to put the gain attenuation back, so on channel 3, so that's 6, and that's going to be back to 1. So now all my gain attenuations are back to 1. I'm going to change the KU value, which is on option number 2, and we're going to change that to 0.72. So that's 0.72, and we've got 336 is our milliseconds is our integration time. So 3 is 336, and there we go. That's 336. And now I'm going to move the compass. Remember, I'm going to hang on to this because it's quite violent when it moves. So we're going to go to the south position. And I'm now going to run the algorithm. Right, and there we go. So let's open this up a bit and just see what we've got there. So we're going to go X, move to the south again, which is on 9. There we go. And we're now going to run the algorithm. So what's interesting here is we're not saturating the integrator at all, and that's because it's so fast now in terms of its response time that it doesn't have time to accumulate huge numbers. So we're not getting quite as big an overswing. So let's just do that again. Let's go exit from that, move to the south position, and now we're going to run the algorithm. So let's have a look. There we go. Let's just pull that in and move that to there and exit that south position. There we go. Run the algorithm. Right. So it does have a big swing, but its response to come back is actually it's very quick because it's on a 1 to 2 ratio. And let's just move this and see actually how it's performing. So it is actually doing what it should, tracking very nicely, and interestingly enough, very little overshoot on this as we're running it. So this is actually a very good control system when you look at it from a small change perspective, but it does give wild swings when we look at this. We can put some gain on this one because in fact what we could do is actually look at it from the total sum going into the servo. Let's just run it again, X, and move to the south position, 9, and let's run the algorithm. There we go. So that's the center line here. That's obviously not the problem in the software because that should have been reset to 0. You can see it being reset here, but it hasn't cleared it at the end of the session. So that's just a bug in the software there. So we're getting that integration. That's the total result going to the servo. So we're actually only sitting at what this is 1 volt per division, so it's not even what that's about. Let's see, that's about 300 going into the servo. We need to look at that from a voltage perspective. So that's 300 millivolts, and you can actually calculate what the actual maths is for this drive here to see what the value is actually going into the actual servo itself. But it's actually a relatively small number. That's everything as regards the control. I don't think there's anything else we can actually do with this. We could play with this for hours and seeing if we could improve it, but in reality, the Ziegler-Nichols method has actually shown us that by using his method, we get actually a very good control system from the basis of maybe not from an extreme transition, like for example going from south to north, but certainly from when you're where you need to be, then the response actually is very good. So the last thing we're going to look at is the anti-windup, and this is a way of trying to get rid of the high values that are in an integrator if the system saturates. Now what you'll notice here is there is no saturation. This is the absolute result going into the servo. So anti-windup will do nothing on this system, and it's responding actually quite well because the whole point of anti-windup is to get rid of the values in the integrator to bring those huge numbers down so that you don't get such big swings. But in order for that to happen, the system has to saturate. Well, as you can see from this, and see from the screen on here, this actually doesn't saturate, and therefore the anti-windup will never occur. Whereas in the previous examples, we did have a small amount of information that went into the integrator that actually saturated, and therefore we can actually look at this, and when you do get saturation, you actually start to take numbers out of the integrator to bring that energy down, and so it doesn't have such fast swings. But we'll look at that in the next video. Okay, thank you very much.